Get started. So hello everyone. Nice to see you all. Um, so today we'll be doing some problems from problem set two. Um, oh, you didn't get one? Could have sworn. Oh, I have an extra one. Wait. Yeah, I have an extra one. Yeah, but like I was, please. Yeah, it's my pleasure. No, it's good. It's all good. It's all good. It's all good. If you have two, now you have two. So it's I'm happy. You have redundancy. Um, okay, good, good, good. Okay. Yeah, so we'll be solving some problems from problem set two in preparation for the midterm, which is next Tuesday. So a bit of information about the midterm. Have you received information about the midterm? You have, such as it's good. Okay, you know the logistics. I mean, in terms of like the content, he didn't tell you anything? Oh, okay. Oh. Sorry, yes. So material is everything about regular languages. So it's about regular languages. And so I did, I think during when I gave the regular expression lecture, I, um, I like kind of promised, I guess, which maybe I shouldn't have, that there wasn't going to be any like conversion algorithms. So that was maybe like a bad promise to make. I tried to convince Jérôme not to put conversion algorithms. Uh, but yeah, I didn't want to. Yeah. So today we're going to be doing a few of those just to get the muscle memory in, because that's the most important thing about these algorithms, just that you kind of know the steps. So we're going to do a few of those. Um, so that's one thing that we're going to do. So algorithms, yeah, you'll see. The other thing that's pretty important for you to master before the midterm is how to use the pumping lemma. So we're also going to look at an example of that today. And also a pretty another pretty important thing is knowing how to use closure properties. So that's also going to be pretty useful for you to know ahead of the midterm. Okay. And I had promised that I would be a bit more explicit about the problem sets. So here's me being a bit more explicit. I think all of the problems in the problem sets are good, but these are particularly good. So something like 8 AB, 10A, and then 12 and 13 from problem set 1, and then 2, 4, 6, 7, 8 are all very good for problem set 2. Okay. Any questions about the midterm, its contents, what to expect? I'll be there. I'll be invigilating one of the classes. So if I'm in the class that you're in, then feel free to ask me questions about like, is zero in the set of natural numbers? Then I'll give you a straight answer. So yeah. How many marks? Yeah, it's over 100. Yeah. Yeah. It's 80 minutes. Yeah. Yeah. Sorry? The time is less. Do you know how many questions are in it? Okay. There's more than three, less than five. So it's doable, I think. No comment. No comment. Okay. So any other questions before we start? No. Okay. So the first thing that I would like to talk about today, like I said, are some algorithms, conversion algorithms about regular languages. In particular, the DFA minimization algorithm. So that's what we'll be looking at. Okay, so in the DFA minimization algorithm, just as like a quick reminder, essentially what's going on in the DFA minimization algorithm is that we have this idea of like distinguishable versus indistinguishable states. PQ. So distinguishability for the purposes of like these notes, I'm just going to use the bow tie symbol. And indistinguishability, I'm going to use this squiggly symbol. Okay. So the idea of the general idea of the minimization algorithm is, you have a very big DFA, maybe it has like some redundant states. So what does redundancy mean in the context of DFAs? It means that you have like states for which you can't distinguish whether you're in one or the other. So it's like the behavior would be exactly the same. So if that's the case, then in the converted minimal DFA, you should take the pairs of states that are indistinguishable and merge them together in a single state. So that's the idea behind the minimization algorithm. So essentially, the general intuition is the minimal DFA will group states together, PQ. So group states PQ together if P is indistinguishable from Q. Okay, so this is the general idea. So then the question obviously becomes, well, how do you find indistinguishable states given a DFA? So there are sort of two conditions that one can check to see if states are indistinguishable. There's kind of like a base condition, which is kind of like the base case of the algorithm. And then there's like a recursive condition, which is kind of like the recursive case of the algorithm. So I'll call this like the initial condition for distinguishability. So although I've been talking about indistinguishability, the algorithm actually works by finding pairs of states that are distinguishable, and all the states that are not distinguishable become indistinguishable at the end, and then you merge them together. So the initial condition for P being distinguishable from Q is if P is an accept state and Q is not an accept state. Right? So clearly that means that they have different roles, right? Because one is causing the machine to accept at that point, and another one's causing it to not accept at that point. Or, of course, I mean, this is like kind of a commutative. It can also mean that P is not an accept state and Q is an accept state. So this is like the base case or the initial condition. And then the recursive condition or the recursive case, the recursive condition is P and Q are distinguishable if, so supposing that, they're both non-accept states or they both are accept states, it doesn't necessarily mean that that makes them indistinguishable, right? Because it's very possible that I have like two states, S and R. They're both not accept states, but maybe they're doing different things, right? So just because they're not sort of different in terms of their type, in terms of acceptability, doesn't mean that they're indistinguishable. So the idea is that pairs of states can also be distinguishable if they lead to distinguishable states, right? So if there exists a letter in sigma such that when you read that letter from P and when you read that letter from Q, you go to pairs of distinguishable states. So the idea is like, for instance, I have S and R, and I know that S reading an A, I go to P, and R reading an A, I go to Q, which is an accept state, right? So even though at the beginning, it might not look like S and R are distinguishable, because P and Q are definitely distinguishable, then S and R also are, because you sort of, they lead you to a pair of distinguishable states. Okay, does this make sense overall, the general idea? So this is the general idea. Now, how do we actually implement it in a conversion algorithm? So we're going to do that in this exercise, where we want to convert the following DFA to its minimal DFA. And just in case you forgot, minimal DFA are unique, right? So it's perfectly fine for me to say the minimal DFA for this regular language because there's only one up to relabeling of the states. Okay. So let's see. I'm thinking whether I should give you some time to try it. You guys want some time to try it? No. That's a very, very confident no. Okay. All right. Okay. Let's go with the confident no, and let me show you how to sort of go about doing it. So the way that we run this algorithm is we create a table. So let's make a table. And the table is going to be like a 2D table where you're going to have all the pairs of like all the pairings of states. So let's list the states. 0, 1, 2, 3, 4. And then Q0, 1, 2, 3, 4. So let's make this a nice table. Okay. So now this table is going to be essentially keeping track of which pairs of states are distinguishable. So you can kind of think of this as like a distinguishability matrix. Distinguishability matrix. Okay, and one trick before you start the algorithm, because you're going to sort of start the algorithm by checking the base condition and then recursing on the sort of recursive condition here, is to also annotate in the margin, are the states accept states or not accept states, because that's going to help. So let's see, Q0 is not an accept state, Q1 is an accept state, Q2 is not, Q3 is, Q4 is not. Okay, and then I mean it's the same idea, like these things are symmetric. Okay. And now the other thing that's going to sort of speed this up a little bit is noticing that actually this matrix is like symmetric, right? It's like lower. So if you just focus on the sort of lower triangular part of the matrix, then it's going to give you the same result as if you focused on the upper triangular part of the matrix. Because distinguishability is commutative. So if P is distinguishable from Q, then for sure Q is distinguishable from P, right? Maybe let me take a question after I start this. I'm sure it is. Okay, sure, yeah. Like in S1 we put the sets which are not accepted states, and in S2 we put the sets, the states that are accepted states, and then divide. Yes, that's another way. I see you've watched one of my videos, it seems like. This is another way to do it. I can't tell you why, but I really think you should also learn how to do it this way. Yeah. So this is like there are many videos online about like how to minimize DFAs. I really think you should like know this one like pretty well. Okay? Okay. But yes, that's another way of doing it. Yeah, you're right. Yeah. Okay. So what was I saying? The matrix is symmetric, yes? And also the other thing is I don't actually have to focus on the diagonal because like I mean I am indistinguishable for myself. So I can also ignore this because it's not gonna like actually help the run of the algorithm. So instead, to make things faster, I can just focus on this here. So this part of the matrix is what I'm gonna focus on. Okay? So now what I'm going to do is I'm going to start marking X's in the table where I see that my base condition is met. Right? So when is my base condition met? When a row is an accept state and a column is not an accept state or vice versa. So for instance, it's the case here. It's also the case here. Let's see. It's also the case here. That's also the case here. It's also the case here. And then also here. Okay. So please stop me if you see a mistake. This seems okay so far, I think. Okay. Okay, so this is like step one essentially. So let's say that step one or the base case was with this black ink. Okay, so this is the base case. Now I'm going to start the actual recursive case. So the recursive case for the first steps, I'm going to take multiple steps in the recursive case. I'm going to talk about the stopping condition later. But so let's do step one, or let's not use blue. Let's do step one of the recursive case in red. Right? So how do I do the recursive case? Well, now I look at all of the states which are not marked, and I check whether they go to reading the same letter, or whether they go to a pair of states that is distinguishable, right? So this is what I'm going to check. So for instance, let me check Q0 and Q2. So I'm doing this cell. I'm checking if I should mark this cell with an X. So to do that, I'm going to do delta Q0 with, let's say, an A. So I'm assuming the alphabet here is AB. Okay. And then delta Q2 with an A. All right. So let's see, delta Q2 with an A, Q2 with an A, that goes to Q1. Okay. And then Q0 with an A. Does anyone see a problem? There's no transition, right? There's no transition. Okay, that was on purpose. So there's no transition for Q0 reading an A. Whenever you see this and you're told that this is a DFA, you kind of have to assume that means that there's actually an extra state and it's a dead state. Okay. So this is actually, there was like a hidden dead state here, which no one told you about. So what that means is I actually have to add a row to this table, right? Because otherwise things are not going to go well. So let's add an extra row for Q5. And this is not an accept state. So this is not an accept state. And let's see, this is an accept state. This is an accept state. So I mark, oh, and I have to do this. So then I mark this guy and this guy. Okay. So I just have to do this extra thing, right? So if you didn't realize this, for instance, like I kind of did, then no worries, just add an extra row at the end. Okay. Okay. So then if we actually do this now, right? So we have this diagram. How visible is this? Pretty visible. Now when I'm at Q2 and I'm reading an A, I go to Q1. And when I'm at Q0 and I'm reading an A, now I go to Q5, right? So I go to Q5. And now let's look in my table. Like, is in my table, do I already know that Q1 and Q5 are distinguishable? Well, let's see, Q1 and Q5, there's an X. So that means they are distinguishable, right? So that means they are distinguishable, right? Which means that I can mark the cell that I started with, so Q2, Q0, with an X. I can mark this with an X. Okay? Does the procedure make sense? Okay, good. So now I'm going to go just a little bit faster. But the idea is always going to be the same. So let's see, Q4 and Q0. So if I'm at Q0 and I read an A, I go to Q5. If I'm at Q4 and I read an A, I go to Q3. Well, Q3 I see is an accept state and Q5 is not an accept state. So that also means that Q0 and Q4 were distinguishable. So I'm also going to mark this. What about Q5 and Q0? So let's see, Q0, actually this one is worth writing. So Q0, when you read an A, you go to Q5. We've already talked about this. And Q5, when you read an A, you go to Q5. So at this point, this is not like evidence for me to mark. So it seems like so far these are actually indistinguishable and I shouldn't mark them for this step. But now let me do the same thing with B, right? Because I have to check, remember the recursive condition, it's such that there exists, right? If there exists at least one, then that means that they're distinguishable. Okay, so let's do it with B. So if we do the same thing with B, then what do we get? Q0 with B, that goes to Q3, and then Q5 with B, that goes to Q5. So now I know, let's look at Q5, Q3, that's distinguishable, right? So I'm going to mark that. Okay. Okay, and then, and so I'm going to mark that. And then let me just keep on going. I'll answer the question at the end of this step. So let's do Q3 and Q1. So Q1 and Q3. So Q1 and Q3, when you read an A, you go to Q0. And from Q1, when you read an A, you go to Q0. So like Q0, Q0 indistinguishable from itself. So that's not evidence for distinguishability. Let's look at Q3, Q1 reading in B. So I go to Q2, and here I go to Q4. Okay, so let me check Q2, Q4 in my table. Q2, Q4 is not marked. So if Q2, Q4 is not marked, then that means that I shouldn't actually mark the thing that I'm actually comparing. So I'm going to leave, so that means that I've checked A and B, so I'm going to leave this unmarked. Okay, I'm going to leave this guy unmarked for this step. Let me do the same thing for Q2 and Q4. So Q2 and Q4, when you read an A, you go to Q1 and Q3. That one's unmarked because I just did it, right? What about with a B? With a B, I go to Q1 and to Q1, right? Q1, Q1, indistinguishable from itself. So again, that means that there's no evidence for marking. So again, that means that this guy is also not going to be marked. Okay, let me finish the whole pass. Sorry. Otherwise, it breaks the flow. At least for me. Okay, Q5 and Q2. Q5 and Q2. So when you read an A from Q2, you go to an accept state. When you read an A from Q5, you go to a non-accept state. So that means that I should actually mark this guy too. So let me do this. Let me mark. And then Q5 and Q4. So Q5 is here. I just talked about it. When you read an A, you go to Q5. Q4, when you read an A, you go to an accept state. So, you know, you have Q3, Q5 here. Q3, Q5 is marked, so I can also mark this step. Okay? And this concludes step one, right? So now I'm going to do this again for the remaining, because I haven't told you the stopping condition. The stopping condition in this algorithm is if from one step to another, there's no change in the table. Okay? So at step one, this is like, so actually let's copy this because we want to remember what was the state of the table at step one. So let's copy this. Let's paste it. Hopefully that wasn't a bad idea. Okay, so this is what my table looked like at the end of step one. Okay. Okay. So now step two, I'm just going to do the same thing. So step two, I'm going to do the same thing. Let me use a different color. So what are the states that are remaining? There's Q3 and Q1. So Q3 and Q1, when I read an A, I go to Q0, right? That hasn't changed since before. Q0 indistinguishable from itself, so that's no evidence for marking. Q3 and Q1, when you read a B, you go to Q4, and here you go to Q2, that's unmarked. So again, that's no evidence for marking. So that means that this guy is still going to be unmarked. And then for Q4 and Q2, Q4 and Q2, you know, Q2, Q4, you read an A, you go to Q3. For Q2, you go to Q1, that's unmarked. So that's no evidence for marking. And then Q2 and Q4, when you read a B, you go to Q1, you go to Q1 in both cases. Q1 indistinguishable from itself, so I also don't have evidence for marking. So that means that I'm done with step two, and this is my table, right? And so you'll notice that this table here is exactly the same as this really tiny table here, okay? Which means that I'm done, right? So because the table at the end of step one is equal to the table at the end of step two, this implies that I'm done. Okay, I'm done, and this is like my resulting table. So, that means that I'm done with the algorithm. But of course, what do I actually want? Is I want a DFA. This is no DFA. So that's the other part of the algorithm that's kind of important is now we have to kind of design a DFA based on this table. So now, let me put this here. Okay, so the last step. So the last step here is to design the DFA. I'll write the minimal DFA based on the table, the final table. Okay, so how do I do this, right? How do I do this? Well, I take so I take, for instance, the states Q3 and Q1, which are indistinguishable from each other, and I put them in a set. And then that set becomes a state. So I get a state, which is the set Q1, Q3. Then again, I do the same thing for the other sort of slots, right? So here I have Q4, Q2, so Q4, Q2, right? They're indistinguishable from each other, and so they should also be in a set, which should represent a state. So that's why I'll circle them. Okay. So I have Q1, Q3 together, Q2, Q4 together. So now all the other states that haven't been grouped so far, they should just be individual states, right? So they'll be individual states. So that leaves me with Q0 and Q5, right? Okay. Okay. So now I've created my states, right, of my DFA. Now, what's going to be the start state? So the start state is going to be the state that contains, because remember now here states are sets, that contains the start state from the original DFA. From the original DFA. So in this case, this tripped me up the first time I did this, but notice here the start state is actually Q1. Okay, so the start state is Q1 and not Q0. Okay, so be careful. Q0 does not necessarily mean that it's the start state. So that means that my start state is this guy. Okay. Okay, so that's the start state. Now, what about the final states or the accept states? So the accept states are going to be the states that contain accept states from the original DFA. Okay, so in this case, what were the accept states initially? They were Q1 and Q3, right? So, okay, which states here contain Q1 and Q3? Well, it's just this one, right? So that means that this start state is also going to be the only accept state. Okay, so now I have my states, and I have my accept states and my start state. The last thing I need is my transitions, right? So how do I do the transitions? So the way I do the transitions, for the transitions, is I essentially just use the transitions from my original DFA, okay? And so, I mean, it's easy to do this when it's Q0 or Q5. When it's a set of states, then the question is, well, which state do you use? Well, one of the sort of lemmas when you prove the uniqueness of the minimization, the uniqueness of the minimal DFA is that it doesn't matter which sort of state you use. The behavior is going to be the same. Right? That's kind of why we call them indistinguishable. So that means that to determine the transition from this state, I can either pick Q1 and Q3 and just see what happens in the original DFA. So let me copy the original DFA. So this is the original. Oh, gosh. Okay, nice. Okay. The unfortunate advantage I have in the tutorial is that I have an iPad. You unfortunately cannot use your iPads in the midterm. Sorry. Okay. So if I'm, let's say, so let's pick Q1 as the representative. If I'm at Q1 and I read an A, then I'm going to go to Q0. So that just tells me that for this state, I'm going to go to Q0. Okay. For when reading a B, well, when I read a B, I go from Q1 to Q2. So that means that I go to this set of states. So that's going to be for B. Then I do the same thing for Q2, Q4. So for Q2, Q4, let's just pick Q2 as the representative. If I read an A or a B, I go to Q1. So that means that reading an A or a B, I go back to this state, right? Then for Q0, if I read an A, I go to Q5. And if I read a B, I go to Q3. So in other words, I go in my minimal DFA, I go to the set of states that contains Q3. And for Q5, well, this is a dead state, so it remains a dead state. Okay. And so now this is my minimal. So now I think I can take questions. So let's go, yes.
Why did we assume that this is going to play?
Why did we assume? Yeah, that's a good question.
There's no transition to it, so you can also bring back the state proof or something or like
Yeah, we could, but yeah, the convention is that if I tell you it's a DFA and for some reason there's a transition that's omitted, it means that it goes to that state. That's just a convention. Yes.
Second question was
Yeah.
distinguishable states are ghosts which don't reach the same state on the same input, or that's not distinguishable. Like
Yeah, distinguishable states are either pairs of states that are different in type in terms of acceptability, or where when you read a letter, when you read the same letter from both of them, you go to a pair of distinguishable states.
different states.
I mean, they must be different for them to be distinguishable, yes. Yes, but it's a recursive definition, right? So, yeah. Yeah. Yeah.
I understand form
Yeah, English is hard sometimes. I feel you.
How would you first of all decide that there are set states in the first diagram? On the second one, how did you make that same decision?
Yeah. So it wasn't very clear. Like there's an in arrow here, which so normally it'll say something like start. Yeah. My bad. Yeah.
And when we do the together, I think one was with the other one, so you say, oh, that's this.
Yeah, because it's the set. So if in the minimal DFA you have set of states, then the start state is the set of states that contains the start state from the yeah.
Say we have like two dead states for some reason, like
Yeah.
like we would never like
Yeah,
say that they're undistinguishable, but that like we could like take one of them away. And like we could minimize more.
If you have, so this is a good question. Like, if you have two or more dead states, then the minimization algorithm has to actually merge them together. If it doesn't, then that means that there's a mistake in your execution of the algorithm. It must. It must. Like, if you have two or more dead states, then the minimization algorithm must merge them together. Why? Because minimal DFA are unique. And I mean, just by definition of minimality. Because if you have two dead states, I mean, if you have two dead states, right? So imagine here I'm going to this guy. So somewhere in my DFA, I'm doing this. And then somewhere in my DFA, I'm also doing this. Right? But I can just merge this together. I can just say, well, instead of going here with whatever letter you're reading, just go there, right? And I can immediately get rid of this state. Yeah?
But, but like I don't see why the algorithm would like because I mean in order to like eliminate a dead end like a dead end state we would have to like
I see what you're saying. I see what you're saying.
distinguishable things and we can't do that.
Yeah, this is a bit of a deep question. Like, can I talk to you after? Okay, because it's I see what you're saying, but it should actually minimize them together.
Right.
Yeah. Yeah.
You're very expensive to work here.
Yeah.
If you, so that's like, I think, all the except states or just one of the except states of the.
Well, yeah. So that's a good question. So the question is, should for the states in the minimal DFA, for them to be accept states, do they have to contain all of the accept states? So, right, something like this. The short answer is no, because it's possible that you have like two accept states that initially are merged together, but then your minimal DFA splits them. Right? In which case, then both of those states are also going to be accept states. And one thing that's impossible in the minimization algorithm is for you to end up with a set of states where you have like Q1 and Q2, where you have an accept state and a non-accept state together in the same state, because they're initially distinguishable. So once you identify something as distinguishable, right? Like once you mark something here, then it's always marked. So it's never gonna like somehow, you're never gonna erase the marking, you know? Yeah, that's right. Yeah, that's right. Yeah. Yes. No, they don't matter. No. You could have, yes. You could have. Yes, absolutely. Yes. Yes. Okay. Nice. Okay. Okay, nice. I think we're good. All right. So excellent. So this was a question about minimizations of one minimization of the DFA, which I believe will be useful in your preparation of for the midterm. Another algorithm which you might have to run by hand is a conversion from an FA to a regular expression. So it's very possible that this is asked of you as well. And so let's look at an exercise where we try to do this. So convert the following DFA into an equivalent regular expression. So in this case, the DFA is just going to be the minimized DFA that we had. But there are some other exercises in the problem set where you can practice some more. So just because I agree that these names are a bit clunky, let me just rename them. Oh yeah. Okay. All right. I mean, this isn't that much better, to be honest. But we want to minimize this, or not minimize, we already minimized. Oh yeah. We want to take this DFA and convert it to an equivalent regular expression, right? So the regular expression that we get should describe exactly the same language accepted by this DFA. Okay. So there are two methods to convert FAs, so DFAs and NFAs actually, to regular expressions. The first one is the K-path conversion algorithm, which I think you've seen in class. I don't like this algorithm. It's very long, I agree. It's not realistic to do in a midterm. And so, and I also don't like it. So instead, I'm going to show you the other way of minimizing or not, I keep saying minimize, converting DFA or just FA in general to regular expressions, the state reduction algorithm. And before you ask, yes, you can use both methods, either one, during the midterm. I mean, you can do both, but maybe don't. Okay, so that's what we're going to do. So you probably haven't actually seen this algorithm. So let me explain it to you at a high level a little bit first. Essentially, this algorithm, you can think of it as like a loop that loops by sort of eliminating states in your FA until you reach an FA that looks something like this, where R is a regular expression. So I'm allowing labels in my FAs to now be regular expressions. Okay. And so essentially, I'm going to sort of eliminate states in my FA until I get something that looks like this. Okay, give me a second. So I'm going to eliminate states in the FA. And when I say eliminating states, I have to do this by preserving or while preserving the logic of their transitions. Okay, so this is a bit vague. Essentially, what the state reduction algorithm does is that it takes any FA and it starts ripping out states from the FA. But to sort of rip out a state from your FA, you kind of have to preserve the logic of the logic that the state sort of allowed in terms of transitions. So what I mean by that is, you know, if you have an FA like, if you have some FA and you have like Q2, which is kind of like an intermediate state that you want to rip out, and you have something like the states Q1 and Q3, to go to Q2 from Q1, you can take an A. Maybe there's a self loop on Q2 with an A, and then to go to Q3 from Q2, maybe there's a B, right? So maybe this is like part of your FA, and what you want to do is you want to like eliminate this Q2, right? You want to eliminate the state, but you want to do this while preserving the logic of the transition that it's sort of allowed, right? Because the idea is that, you know, you remove the state such that you get closer to something that looks like this, but you also don't want to lose information, right? And so how do you do this? Well, the crux is just you essentially use regular expressions as the labels of the transitions. So when you eliminate this, right? So when you eliminate this, there's still going to be a transition from Q1 to Q3, but now it's going to be represented using a regular expression. So in this case, it's going to be the regular expression that recognizes strings that look like A, any number of A's, and then B, right? Because that's sort of the logic that Q2 is allowing, right? Q2 is allowing for your machine to get from Q1 to Q3 by letting it read an A, then any number of A's, and then a B, right? So that's why instead of having this intermediate state, what I can do instead is create a direct edge or a direct transition where the label now is A star B, right? If, for instance, in my original FA, I had something like a direct connection from Q1 to Q3 with maybe, I don't know, BB star. Maybe there's like already a regular expression because I had eliminated something else before. Then what I do is I say, well, you know, I can go from Q1 to Q3 with BB star. And now I can also do it by reading A star B. So then, you know, I can do either or. So that's just a disjunction. So then I just use the plus operator from the regular expression sort of syntax, right? So instead, I get Q1 goes to Q3 by either reading A star B or B star, right? Okay, so this is kind of what I mean by preserving the logic, right? It was very vague at the beginning, but hopefully you're starting to get the idea. Now, what if, what if there are more states that go through Q2, right? So what if there's like Q5 that goes to Q2 with a B, and then maybe Q6 that you can get to from Q2 with, let's say, A star, right? Then now what you have to do when you sort of remove Q2 is, well, you have to preserve the logic of transitioning from Q1 to Q3 with Q2, but also every other sort of combination. So you have to consider, going from Q1 to Q3 using Q2, but also going from Q5 to Q3 using Q2, right? So then you rip this out, and instead you have a transition here, okay? Then again, for instance, you would also have to consider going from Q1 through Q2 to Q6. So if you eliminate Q2, then you have to add the transition that's maybe here A star, right? And you have to do this for every single sort of way to go through the state that you're ripping out, okay? So this is the general idea. So let me just write something. So essentially the general idea is to remove one state at a time. Preserving transitions for all pairs of states. That use the state you're eliminating. Yeah, so you remove one state at a time, preserving transitions for all pairs of states that use the state you're eliminating via regular expressions as labels for the transitions. So hopefully this is a somewhat coherent sentence. Okay. Yeah, so I think you had a question first, and then.
Kind of the question was.
Okay.
You need a DFA.
No. Yeah, no. So the question is, do you need a minimized DFA to run this on? No. You can actually run this on an NFA as well with epsilon transitions. Yeah. So we'll see actually how to do that in a second. Yeah.
Either go to A star, B star, or B star, right? That's what the number of them get.
No, or. Yeah, or. Yeah. Okay. So now let's actually try to run this conversion algorithm. Do I still have this saved? Ah, the ugly one. But so what was the point of? Okay. Anyways. Okay. So we're gonna run it on this guy. Now, remember what I kind of want to, so my like stopping condition, the goal I kind of want is to get to something that looks like this, right? But this is kind of a problem because it's possible. So you haven't seen these types of NFAs in this class, but it's actually possible to have multiple start states in different types of NFAs. And it's also possible to have multiple accept states, right? So how do you get, a single start state and a single accept state? Well, you just use epsilon transition, okay? So before you start the algorithm, this is something that you have to do to sort of, as a kind of like pre-processing step. So step 0 is to convert the FA such that it contains one start state and one accept state, right? So how do you do this? Well, if you had multiple start states, then you just create a single start state and you have epsilon transitions. And if you have multiple accept states, then you essentially you make these non-accept states and you create epsilon transitions to a single accept, right? Okay. So that's what I'm going to do to this guy here. So let me recopy it. Okay, so let's not make this an accept state anymore. I have my start state now. This is my new start state. I go using an epsilon to this state, which used to be the start state. And then from this guy, I also go to a new accept state because this guy also used to be an accept state. Okay. And now at this point, I can start sort of ripping things out. So immediately, one thing that I see already is that I have a dead state. So for dead states, I can just rip them out and, nothing is actually going through the dead state and coming back, right? So that means that I can just take it out and it won't affect the final regular expression. So I'll call this step 1 because this was step 0, right? This was step 0. Step 1 is removing dead states. Okay, so I've removed my dead states, or so I claim. So now the new machine I have is this. Okay. It's a funny working machine. Yeah, let me finish. Yes. Yeah, go ahead. Step 0, I'm just creating a single start state and a single accept state, right? And to do that, well, if I have multiple start states, then I make a new state and I create epsilon transitions to each start state, right? Because this person. Yeah. Because suppose initially I had like 3 accept states. Then if I just want one accept state, I make these not accept states, and then I create epsilon transitions to the accept. Yeah. 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 Oh, that's another good point. Yeah, thank you. Yeah. And also the accept and start states should be different. Right, they should be different because I'm trying to get to something that looks like this, right? Where if this is a regular expression and I'm like, this is an FA that has a regular expression as a label. And then I ask you, what's the equivalent regular expression to this? Well, then you're just gonna be like, well, it's just R, right? Because that's the only way that you can get from the start state to the accept state. Yeah? So that's why you need sort of a single start state, a single accept state. They have to be different so that you get something like this at the end. If they are the same, then you have to split them like I did here. Right? So here they're the same, right? So now what I did is I created a single start state, made an epsilon transition, and then I created a single accept state, made an epsilon transition. And now this is no longer an accept state. Yeah? It's just a regular vanilla, no frills state. Yeah.
There, assuming that on the final state, like it goes with the, right?
Yeah, there's no outgoing transitions.
Okay.
Yeah, no outgoing transition. Yeah. Okay. So after doing this preprocessing that we've just talked about, let's actually start doing like intermediate state deletions. So step 3 is going to be deleting, or step 2, deleting intermediate states. Okay, so let's delete, let's say this one first, right? So if I want to delete Q0, then I have to preserve the logic that it allowed. Well, what does Q0 allow? It allowed me to go from this giant guy to Q0 and back to it, right? So that means that if I'm removing this, then I have to create a self loop with AB as the transition, right? Because I can use Q0 to loop back to myself, right? So let's do that. Let's copy this. Let's remove this. Let's get A, B. B. Okay, so I've deleted that state. Now let's delete another one. I'm obviously, well, not obviously, but I'm never gonna delete the start or the accept state because I need them. It seems kind of like you also kind of have to do a bit of like look ahead or sort of forward thinking. It's probably kind of a pain to delete this right now. So it might be easier to just delete this because it has a single like ingoing and outgoing edge. So that's what I'm going to do. Let me please let me take the question at the end. Okay, please. Thank you. I'm almost done. Okay. So if I delete this, right, then I have to preserve the logic. Well, what's the logic that this guy allows me to have in my machine? Well, it allows my machine to go from here and then to go back to itself by reading by reading a B, and then either an A or a B, right? So if I remove this, guy, then what I have to do is add to the self loop B and then A or B, right? So now I'm going to delete this. Yes, you also could. Yes, yes, yes. You also could. Yes. Okay. So now I have this guy. Why does this look funny? I don't know. It just does. So I have this guy, and now I want to delete this huge state, right? So to delete this huge state, I have to account for like the logic that it allows me to have in my machine. Well, what's the logic? It essentially allows me to go from here to here by looping many times, right? Well, what is looping many times in terms of regular expressions? Well, it's a star operator, right? So instead of having to sort of go through this state and loop any number of times, I can just write this. I can just write this as I read the empty string, then I read B, A plus B, or AB any number of times, and then I read an empty string, and then I jump to the accept state, right? Okay, and then this looks like a regular expression to me, which is great because that's what we were going for. So then the equivalent regular expression is this guy, right? Because notice this was like the stopping condition that I was looking for. And remember from the sort of regular expression lecture, if I have something like R empty string, or like the empty string, the regular expression that denotes the empty string, then this is the same as R, right? So that means that I can simplify this a little bit and do B, A plus B plus AB whole star, okay? And now this is the equivalent regular expression. And let me just check that this makes sense if we go back to the DFA. So where's the DFA? Okay, this guy. Okay, so does this make sense as being like the regular expression that's equivalent to this DFA? Well, what is this regular expression telling me? It's telling me that my string can be, B then A plus B or AB, and that can happen any number of times. Well, let's see. Okay, I'm at my start state. I can read AB, right? So I can have AB. Then I can maybe use this. I can read B and then have A or B. So I can have B and then A or B. And then I can repeat this any number of times, interchanging any number of times, right? And so this is exactly what this guy is describing. So yes, it does seem like these two are equivalent in terms of describing or accepting a regular language. Okay. So now, are there any, and this is how you sort of use the state reduction algorithm to convert sort of any FA to regular expression. I have some other videos that I will post because like this is a fairly simple-ish example. I have some examples of a bit more involved conversions. The ones in the problem set are also a bit more involved. So you'll be able to practice them a bit more as well. Okay. Okay. Are there any questions? Yeah, yeah.
AB and ABI, you sort of did that, you put all the loops into the star.
Yeah, yeah, yeah.
There's no countering loops in the intermediaries there.
No, you do. So you do count, like if you have, so the question is, loops, in intermediate steps. This is an important question, right? So if you have something like, this, something like this, right? And you want to delete this, right? Then you do something like A, then all of the thing in the self loop, whole star, and then B.
Yeah, but if you go, the,
Just tell me when.
yeah, yeah.
Which one am I supposed to look at? Okay. Yeah.
You could go B and then you go A or B. But you can also do that, like, whether that, it would be B, A, and then B, B. But we don't count that as typing. And we do that.
No, sorry, no, yeah. Yeah, you just assume that the self loop is gonna, like this information of looping sort of persists, right? Up until the end. Okay, right? Because you have, like, it's in a self loop, and because, sorry about that. Because the self loop is going to get converted to a star, then it's okay. Yeah, okay. Okay, any other questions? Yeah.
You go to this again.
And I have to move on. I can talk to you offline. Yeah. I need to do pumping lemma. I like, like I really, for the sake of the midterm. I have to do a pumping lemma question. Okay. Okay, good. So let's do a pumping lemma question. So in this question, so this is actually a question from the problem set. So this is problem set 2, question 6b. We want to prove that the following language is not regular. Okay, so where the language is ANBM, NM is in the set of natural numbers, N is less than M, N is even, and M is odd. Okay. So intuitively, why is this not regular? Because of like this condition, right? Because this is saying, I have to remember how many A's I've seen and then check that I have more B's than A's, right? So this kind of requires some memory, which FAs only have a finite amount, but really this N could be like arbitrarily large. So if you actually wanted to make an FA for a language like this, then you would need an infinite number of states, which, you can't have because it has to be a finite automaton, right? But that's not a proof. Please don't write that in the midterm. What you should write instead is a pumping lemma. Okay, so that's what we're going to do. We're going to use using the pumping lemma. So just as a reminder, what does the pumping lemma say? The pumping lemma says that if L is regular, then there is some pumping length such that for every string in L, which has length at least the pumping length, there exists some decomposition x, y, z of W, where the length of the first part of the decomposition xy is at most p, and the length of the middle part of the decomposition y is at least 1. So there exists this decomposition where no matter which I you pick, you're going to get that x, y, I, z. So if you pump y I times, that's why it's called the pumping lemma, because you're pumping, you're sort of injecting y into the decomposition I number of times, then this will remain in L. right? This is what the pumping lemma says. Yes, yes, yes. So in this case, yes. In this, in this case, 0 is in the set of natural numbers. Yes, yes, yes.
So you can say I.
Yes, thank you. Let's do that. Greater or equal to 0. Yes, but I has to be an integer, but hopefully I don't have to specify it. Oh God. Yeah.
There exists inside things,
Yeah.
but like.
Yeah, this actually, yeah.
It can be anything
Yeah, it can be anything.
from one like infinity and.
Yes, as long as there exists at least one. Yes, yes. Okay. So that's what the pumping lemma says. Now, how do you use the pumping lemma to show that a language is not regular? Well, this is like, if regular, then this. So then you can do not this, then not regular, right? You do the contrapositive. So you just do the contrapositive. So what is the contrapositive? It's for every p in the set of natural numbers, there exists a w in L where a w has length at least p, for which it doesn't matter what the decomposition is. You can find at least one I, you can find at least one I such that x, y, I, z is not in L. Okay. And so if you have this, right? So if you have this, then it implies that L is not regular. Okay, just by the contrast. Okay. So this still looks like a monster of a propositional statement. So to make this a bit easier, the way that you can use this statement to show that a language is not regular is you can think of it as, you know, you want to satisfy this statement. So to satisfy the statement, you have an opponent. You're playing a game against an opponent. Your opponent plays the for all classifier or quantifier, and you play the existential, right? And so you win the game by defeating the opponent. And in this case, if you're playing the existential quantifier, then winning means that you can find an I for which this is true, where it doesn't matter whatever your opponent played, you can always kind of find a strategy to defeat them. So this is the general idea. Okay. So how am I going to actually implement this? So what did I say? So imagine for all is your opponent and you are the existential quantifier. To prove L is not regular, epsilon should defeat epsilon. The existential should defeat the for all, right? This is the general idea. And you can use this kind of strategy in the midterm. It's perfectly acceptable. If you don't want to use the strategy and you want to be you want to do something else, then that's also cool. Just make sure that it's correct. Okay, so how is this going to work, right? Because I want to do this for L, right? So I want to do this for this particular L. So this particular L is A and BM, where N is strictly less than M, and it's even and M is off, right? So the way that this works is it's the for all's player's turn first, and then it's your turn. And then it goes back to for all, and then it's your turn. So the for all player is just going to pick some natural number P, right? They're your opponent. You have no idea what they pick. They just pick some P in the set of natural numbers, right? You have no control over what P is. Remember that. It's very important to remember that. Then what you have to do is you have to play the existential quantifier. And so you have to pick a particular string W, right? So you have to pick a particular string W. So I need to pick some W in L, where the length of W is at least P. Okay. So, you know, there are many W's that one could pick. Some might be correct and some might be incorrect. And even for the ones that are correct, there are some that are sort of better in terms of the strategy than others. So for instance, right, there are many strings that kind of satisfy this condition. So you could pick A power P, right? Yeah, yes, you can. Maybe you can, yes. But let's just, yes, you can also pick A to P.
Like we can. Plus one.
Yeah, what are you doing, man? You're giving away the whole thing. What the hell? Okay, let's go step by step, yeah? Not everyone is as advanced. So let's pick W is A power P, right? So you can pick this, right? But in this case, this is not a correct choice of W. Why? Because, well, this isn't even in L, right? Because here P is in the set of natural numbers, and here, like, technically it's B power 0. So you have something like P is strictly less than 0, so that's false, right? So this would be an incorrect choice. Like, even though it satisfies this, it doesn't satisfy this. Okay, so let's try something else. Like I need to have the B's to be more than the A's. So one natural thing that one might think of is, well, let's just have one extra B, right? So AP, BP plus 1. Right, so here the length is 2P plus 1, so it's definitely greater or equal to P. Now, is W in L? Not necessarily, right? Not necessarily. So not necessarily. Because P could be even, right? It's very possible that your opponent picked P as, 4, right? In which case this would be great. This would work. But you have no idea what your opponent picked, right? So your opponent could have also picked P as odd, right? And so if they had picked P as odd, then this would not satisfy this condition here in the language. So then you also can't pick this because you're not guaranteed that this condition is going to hold. So now if I have a natural number P and I want to make something that's like, some even number and then some odd number, and I want the odd number to be greater than the even number, then a good idea, which someone already had, is something like A 2P, B 2P plus 1, right? So because now this is definitely even and this is definitely odd by definition of what it means to be even and odd. And 2P plus 1 is definitely strictly greater than 2P. And the length of the string is 4P plus 1, which is definitely greater or equal to P. Okay. So that means at this point, I've like done a good job because I've sort of satisfied all the conditions that I needed. Okay. So it's very possible that you pick a string that's correct here, but then when you go back to your opponent's term and then your turn, you find that actually the string doesn't work. You can't find an I. In which case you kind of have to backtrack and choose a different W. Okay. So just by doing a few like practice rounds, by trying a bunch of different problems, you get an intuition as to like which are good and which are bad choices of W. So this is probably going to be a good choice of W. Why do I think this? Because, well, let me show you why I think this. So I finished my turn. Now it's the for all players' turn, right? So what the for all player does is that they decompose W into X, Y, Z, where you don't know what the decomposition is, right? So you don't know what X, Y, Z will exactly be, but you do know that the opponent has to follow the rules of the game. And the rules of the game are that X, Y is at most P, and Y is at least 1. Okay, so this is actually quite helpful to know. Why is this quite helpful to know? Because if W is A power 2P, so I have 2PAs, and then I have 2P plus 1 Bs, right? And I know that this string is getting decomposed as X, Y, Z, right? Then actually, because of the way that I picked the A's, because I picked the A's such that they had, such that there were at least PAs, then what this tells me is that the XY has to be within the first PAs, right? And so that's kind of useful information. So I know regardless of what the decomposition is, I know that xy is going to be some number of a's. So let's say a power k, where k is at most p. And I also know, so I know this about xy, and I also know that the y's are going to be something like a power t, where t is at least 1. Okay? And then the z, right? So the z is just the rest. So I can just say it's like a power 2p minus k, and then b power 2p plus 1, right? So, like this is the x, this is the y, and this is the z. Okay? Okay. And this is like, I mean, the opponent already made their turn they already sort of played their turn by decomposing. I'm just sort of thinking to myself, well, what's the likely decomposition? I don't know what it is exactly, but I have like um, uh, ideas about the ideas about the decomposition in general, right? So I know that y has to be a power t, where t is at least 4. And so that's going to be quite useful when it comes back to my turn, right? Because now when it's my turn, I need to pick an I, which is greater or equal to 0, such that x, y, I, z is not in L, right? Well, what is x, y, I, z? So if I call x, y, I, z, wi, then x, y, I, z is x, y, I, z, right? Well, I'm sorry. Wi is x, y, I, z. So y power I, that's just repeating y I number of times. Then I have z, right? So what's going on is, if I is equal to 1, then I have the original string, x, y, z. If I is equal to 2, then I have x, y, y, z. So that means that if I have x, y, y, z, I'm like injecting into here an extra ta. That's what's essentially going on if I do that. So that's kind of useful to know. Why is that useful to know? Because remember, what's the condition of the language? It's that the number of a's should be strictly less than the number of b. But the xy, right, is some a's, and in particular, the y is some a's. So if I inject an additional y here, what's going to happen? Let's see. So if I inject an extra y and I get y squared, so I get x, y, y, z. And so this means that I'm adding an extra at to the string. What was my string? A to p, b to p plus 1, right? And in particular, I'm adding these TAs in here within the first sequence of A's, right? So that means that my resulting string is a power 2p plus t, b power 2p plus 1, right? Okay, so now I think I'm actually quite happy with this move. Why am I quite happy with this move? Because I know that t is greater or equal to 1. So then 2p plus t, this is greater or equal to 2p plus 1. And so then it's clear that W2 is not in L because the condition here was A n bm, where n is strictly less than m, right? Because the condition for L was, A n bm, n strictly less than m, right? But now I no longer have n strictly less than m. I have 2p plus t is greater or equal to 2p plus 1, where 2p plus t is like the exponent for a, and 2p plus 1 is the exponent for b, right? So now I was successfully able to find an I for which my pumped string is no longer in the language, and so that means that I satisfy this statement. So therefore the contrapositive of the pumping lemma is satisfied. L is not regular. Okay, and that's how you use the pumping lemma.
I don't understand this versus the one.
If you don't like the me versus opponent thing, then you could just think the for all is like, suppose P is some arbitrary natural number, and then the existential is you just pick a particular string or I, basically. So like the opponent, like the for all, this is like, suppose P is arbitrary. Yeah, P is some arbitrary natural number. And then the existential is like picking some particular thing. Right? So here I picked a particular string based on an arbitrary P. And here I picked a particular I based on an arbitrary decomposition. The first thing, sorry, I missed the last part. Yeah. That's the thing you're doing. So what we're doing is we're satisfying this statement. Okay, thank you. Okay, any other questions? No? Nice. Yeah.
What's the real world?
The real world implication is the real world implication of the pumping lemma is that you need at least some data structure that has memory to recognize the language. Yeah. So we'll see when Jérôme talks about like stacks and stuff, you'll see what I mean a bit more. Yeah. All right. Thanks. Thanks a lot for coming. I'll see you on Tuesday. I'll also post extra videos for the things that I can cover today.